This is the last of the special functions that we're going to develop here. Find the Maclaurin series for the quantity 1 plus x to the k, where k is any real number. Well, if f of x is equal to 1 plus x, the quantity to the k, then f prime of x is equal to k times the quantity of 1 plus x to the k minus 1. F double prime of x is equal to k times k minus 1 times 1 plus x, that quantity, to the k minus 2. F triple prime of x is equal to k times the quantity k minus 1 times the quantity k minus 2. 1 plus x to the k minus 3. That's enough of that. Now we're going to generalize this and say that the nth derivative of f of x is equal to k times k minus 1 times k minus 2 times times k minus n plus 1 times x, times 1 plus x to the k minus n. Now, before we go on, what's about this n plus 1? What is this? Well, look, when it was the first derivative, I had k minus 0. When it was the second derivative, I had k minus 0 times k minus 1. That 1 is 1 less than the second derivative, right? The 2 for the second derivative. For the third derivative, the last factor that I ended up writing down with k was k minus 2. So when n is 3, k minus 2. So that k minus is going to be 1 larger than the derivative itself. If that didn't make sense, stare at these, write down some numbers. It will make sense, trust me. Evaluating each of these at 0, because we are talking about the Maclaurin series after all, we have that f of 0 is equal to 1. F prime of 0 is equal to, well, now look, see, the reason f of 0 is 1 is because we put 0 in place of x, right? So for f prime, put 0 in place of x, you got 1 to the k minus 1. That's going to keep happening. So f prime of 0 is k. F double prime of 0 is k times k minus 1. F triple prime of 0 is k times k minus 1 times k minus 2. All we're doing is picking up those coefficients with k. This generalizes. The nth derivative evaluated at 0 is just the k, k minus 1, k minus 2, k minus n plus 1 all multiplied together. Now remember, we've been developing series that have terms. The nth derivative evaluated at a, in this case a is 0, divided by n factorial. Those are the coefficients of our power series expansions, right? Our Maclaurin series expansions. In the case of this particular series, these numbers are called the binomial coefficients and are denoted parentheses k on top, n on bottom, no fraction bar. It looks like a fraction without the fraction bar. Also looks like the notation for a combination. You know what I mean? Like combinations and permutations, that combination. The result here, folks, is that 1 plus x to the k is equal to the sum as n goes from 0 to infinity of the binomial coefficients kn in parentheses x to the n. Expanded, this looks like 1 plus kx plus k times k minus 1 over 2 factorial x squared plus k times k minus 1 times k minus 2 divided by 3 factorial x cubed plus Now the general term k times k minus 1 times k minus 2 times k minus n plus 1 divided by n factorial x to the n plus This is an infinite polynomial. We have seen things that look kind of like this before, not in the context of power series, but look at this. Each successive term has one more factor than its predecessor. The ratio test will show that this converges if the absolute value of x is less than 1. What we've just developed is the binomial series. This holds for all exponents k in the real numbers, not just whole numbers, not just rational numbers. If, however, k is a positive whole number, then if n is greater than k, at some point we'll have k minus k as a factor. So the series will be finite. And the result agrees with the binomial theorem, the one that you would have seen when you saw Pascal's triangle in a way previous class. Maybe not too way previous, but in a previous class anyway. Now, folks, we have developed through this series of videos a lot of series. And they are summarized in a table in your textbook. We have the series for 1 over 1 minus x, for e to the x, the sine of x, the cosine of x, the inverse tangent of x, the natural log of 1 plus x, and now the binomial expansion, 1 plus x to the k, where k is any real number. We also see here the radii of convergence. I do not expect that you will have memorized all of these. What I do hope is that you'll remember which of these series we have in this table, and as they pop up, you can pull them from this table. Unless the directions say use the definition. If that happens, then yeah, I gotta start taking derivatives.